Whenever I see those incredible pictures of spiral galaxies out there in the universe, it kind of makes me wonder, how do we even know what our own galaxy, the Milky Way, looks like from the outside? I mean, we're stuck right here in it.
You've hit on a really fundamental question in astronomy, figuring out something as huge and complex as a galaxy when we're plunked right inside it. But it's pretty amazing how much we've been able to figure out, kind of like putting together a puzzle, but from the inside out.
Okay, so let's try to put some pieces of this puzzle together then.
Yeah.
We always hear the Milky Way described as this barred spiral galaxy, but what does that really even mean if we're trying to picture it?
So think about a giant whirlpool, but like cosmic sized. That's our galaxy in a nutshell. Now, the barred spiral part just means that instead of having just one super bright center, there's this elongated bar of stars running right through the middle. Then, those spiral arms, kind of like the one our sun sits in, they stretch out from the ends of this bar, which is what gives us that classic swirling shape we see in pictures.
So it's not just a random scattering of stars, but this huge, organized system we're all a part of. And when we say huge, we're talking about the Milky Way stretching an unbelievable 100,000 light years across, right?
That's right, 100,000 light years. To give you an idea of how massive that is, imagine trying to count every single star in the Milky Way. Let's say you could count one star each second, every second without a break.
Okay, I'm already tired just thinking about it.
It would end up taking you over 3,000 years. And that's just an estimate, because there could be tons more stars hidden within our galaxy that we can't even see yet.
Wow. Okay, that really puts things into perspective. But we're not just located randomly in this giant spiral, right? We're in a specific area called the Orion Arm, about 26,000 light years from the center of it all. So what's so special about our little corner of the Milky Way?
That's a great question, and it gets to the core of how galaxies actually grow and change over time. See, those spiral arms aren't just pretty features, they're more like cosmic factories, churning out new stars all the time.
Cosmic factories. Okay, now I need to hear more about this.
So imagine those spiral arms as places where you find the most gas and dust, basically the raw ingredients you need to make stars. All that material gets packed together really tightly in these arms, and that squeezing, that compression, it's what kickstarts the birth of new stars. Being in the Orion Arm means we're surrounded by these stellar nurseries, places where stars are constantly bursting into existence.
That totally explains why we see those amazing pictures from telescopes, those dazzling nebulae glowing with baby stars. It's like a never-ending fireworks show happening all around us. But speaking of what holds the galaxy together, there's something incredible hiding in the very heart of the Milky Way, right? Something with incredible gravity.
You're talking about Sagittarius A, the supermassive black hole that sits right at the center of our galaxy, and it really lives up to its name. It's a true gravitational giant with a mass millions of times greater than our sun.
Millions. I have to admit, when I think of a black hole, I always picture something incredibly dense, but also tiny. How can something be both that massive and still a black hole?
That's a common misunderstanding. While the black hole itself is incredibly compact, its gravitational pull reaches far and wide. Think of it like this, a tiny marble, but with the weight of an entire mountain. That's kind of what we're dealing with here.
Okay, now that's a mind-bending visual. So even though it's relatively small, Sagittarius A's gravity basically calls the shots for how stars and gas move across the entire galaxy.
Exactly. You could say it's like the conductor of an orchestra, but on a cosmic scale, making sure everything moves in sync. Even though it's invisible and massive, it's running the show.
So we've been talking about this supermassive black hole, this gravitational giant that's holding the entire Milky Way together. It's mind-blowing to think about, but it also makes me wonder, how do we even know all of this? Man, we can't actually see a black hole directly, can we?
You're right, we can't see a black hole directly, but that's part of what makes science so amazing. We can uncover the universe's secrets even when they're hidden from our view. One of the ways we've been able to study Sagittarius A and map out the Milky Way is this clever technique called stellar parallax.
Stellar parallax. Okay, I think I've heard of that, but could you give us a little refresher?
Of course. Imagine you're holding your finger out in front of you and close one eye and then the other. See how your finger seems to jump back and forth a little against the background? That's basically parallax in action.
Right, right. Our perspective changes depending on which eye we're using to look.
Exactly. And the same idea applies to stars. As the Earth goes around the sun, our viewpoint of nearby stars, it shifts just a tiny bit against the backdrop of those stars that are much farther away. By very carefully measuring these teeny tiny shifts, astronomers can actually calculate the distances to those closer stars.
So it's kind of like cosmic triangulation then.
Uh,
We're using Earth's orbit as this measuring stick to figure out those huge distances to stars in the Milky Way.
That's a great way to put it. And the best part is, this technique doesn't just tell us about individual stars, it helps us map the structure of the whole Milky Way. It reveals the spiral arms, the central bulge, even hints at the presence of stuff we can't even see, like dark matter.
Wow, that's pretty incredible. But I'm guessing parallax only works for stars that are relatively close to us, right? What about those objects that are way, way out there, or things we can't even see with our most powerful telescopes? How do we study those?
That's where another really cool technique comes in, spectroscopy. It lets us study the light from these incredibly distant objects and kind of decode their secrets.
Spectroscopy. Okay, that one sounds a little intimidating, to be honest. Could you break it down for us?
You know how in science class you probably shined a light through a prism and saw it separate into all the colors of the rainbow, right? Each of those colors is a different wavelength of light. When astronomers study the light from a star or a galaxy, they use an instrument called a spectrograph, and it basically acts just like that prism, splitting the light into all its individual wavelengths.
Oh, right. I remember doing that. But what does that actually tell us about this star or galaxy? What are we looking for?
So here's the really cool part. Every single element in the universe, it has its own unique fingerprint, a specific pattern of wavelengths that it either absorbs or emits. And these fingerprints, they show up as either dark or bright lines in that spectrum of light we were talking about.
So by looking at those lines, astronomers can tell what a star is made of, even when it's like unbelievably far away.
Exactly. We can figure out its chemical composition, its temperature, even whether it's moving towards us or away from us. It's almost like we're reading a cosmic barcode. And there's even more. We can also use radio waves to study the universe.
Radio waves, you mean like the kind we use for music and communication?
Exactly. A lot of objects out in space, things like huge clouds of cold gas, they actually emit radio waves, which are invisible to our eyes. But radio telescopes, they can detect those waves, and that allows us to map things like where all the hydrogen gas is in the Milky Way, which is a really important ingredient for making new stars.
Wow, so we're using this whole spectrum of tools, from visible light to radio waves, to piece together this amazing story of our galaxy. And speaking of stories, we talked about the future of the Milky Way earlier, and I have to admit, the idea of the Milky Way actually colliding with Andromeda is both, like, totally mind-blowing and a little bit terrifying. Another galaxy hitting ours, it sounds like something out of a movie.
It's definitely dramatic, no doubt about that, but it's also totally natural when it comes to how galaxies evolve over time. Andromeda, which is our closest galactic neighbor, it's actually hurtling toward us right now at a speed of about 250,000 miles per hour.
250,000 miles per hour. Wow, okay, that's really hard to even comprehend. But, I mean, what would that even look like? In a few billion years, when this collision happens, what are we going to see?
You have to think of it like a slow-motion collision, at least on a cosmic timescale. So as the two galaxies get closer and closer, their gravity starts to mess with each other's shape, pulling out these long streamers of stars and gas. And when those gas clouds collide, boom, you get these huge bursts of new star formation. The night sky would be unbelievably bright.
Well, so a totally brand new night sky. It's hard to even imagine that. But
Right.
what about our own solar system, our little corner of the Milky Way? What happens to us in all of this?
That's the thing. It's really tough to say for sure, but some of the simulations that astronomers have run, they suggest our solar system will probably get tossed around a bit during the merger. We might get flung out to a totally different part of this new combined galaxy, or even, and this is wild, ejected out into intergalactic space.
Wait, ejected, like out into the emptiness between galaxies. Now that's a thought. But even if we end up with a new cosmic address, what about this collision itself? Wouldn't stars be crashing into each other left and right?
That's a common misconception. While we call it a collision, it's more accurate to think of it like a merger. The distances between stars are so vast that actual direct collisions are incredibly rare. It's more about the gravitational dance, with stars getting flung around and their orbits changing over billions of years.
Okay, that does make me feel a little bit better. But still, this whole galactic merger thing, it just raises so many questions like, what will this new galaxy even look like? Will it still be a spiral like the Milky Way and Andromeda, or something else entirely?
Those are some of the big questions that astronomers are trying to figure out right now. They're using simulations and looking at other galactic mergers happening out there in the universe to try to get some answers. What we do know is this. The Milky Way, the way it looks right now, well, that's going to be gone, and a new, larger galaxy will be born out of this merger. But don't worry, this transformation won't happen overnight. It's going to play out over billions of years.
It's wild to think about the Milky Way and Andromeda becoming this whole new galaxy billions of years from now. Really makes you realize that the universe is always changing, always on the move.
Mm.
But as if galactic mergers weren't enough to wrap our heads around, there's another layer to this story. We've been talking about everything we can actually see in the Milky Way, like stars, those gas clouds, black holes. But what if I told you that all of that might just be a tiny piece of what's actually out there?
You're talking about one of the biggest mysteries in astrophysics today, the mystery of dark matter and dark energy, stuff we can't see.
Exactly. These are the things that make me feel like I've wandered into a science fiction movie. Can you even explain what dark matter and dark energy are? Or at least what we think we know about them so far.
Okay, so let's start with dark matter. Imagine a merry-go-round, right? You'd expect the horses on the outer edge to be moving faster than those closer to the center, yeah.
Yeah, it makes sense. They're going a longer distance in the same amount of time.
Exactly. Now, let's take that same idea and apply it to galaxies. So stars that are farther out from the center of the galaxy, they should be moving slower than those closer in, at least if we're just looking at the visible stuff and how gravity works. But, and here's the big mystery, when astronomers actually measure how fast those outer stars are moving, in galaxies like our Milky Way, they're going way faster than they should be.
So there's something we're not seeing, something giving them an extra gravitational push.
That's the leading theory. Astronomers call this mysterious stuff dark matter because it doesn't give off light, it doesn't absorb light, it doesn't reflect light. Our telescopes can't see it at all, but we can see how it affects the stuff we can see through its gravity.
Okay, so it's like this invisible hand, this dark matter, shaping the way galaxies move and behave. But what about dark energy? Where does that fit into all of this?
Ugh, dark energy. Now that's a whole other level of mystery. For the longest time, astronomers thought that the expansion of the universe, it was slowing down over time because of gravity. You know, like if you throw a ball up in the air, eventually it's got to come back down. But then in the late 1990s, they started looking at these really distant supernovae, and those observations showed something totally unexpected. The expansion of the universe isn't slowing down, it's speeding up.
It's speeding up. So instead of gravity pulling everything back together, there's something else pushing it apart and getting stronger as it goes.
That's exactly it. This mysterious force, it's what we call dark energy, and honestly, we still have no idea what it actually is. It seems to be something fundamental about space itself, like it's woven into the fabric of the universe. And get this, based on how fast the expansion is accelerating, scientists think dark energy makes up a whopping 68% of the total energy density of the entire universe.
68%.
Yeah.
Seriously, so we've got dark matter holding galaxies together, dark energy pushing everything apart. What does that leave for the normal matter, the stuff you and I are made of,
Yeah.
everything we can actually see?
You're hitting on a really humbling realization. All the stuff we can see, every star, every planet, every galaxy, even us, it only makes up about 5% of the total mass and energy in the universe. The other 95%, yeah, that's the mind-blowing realm of dark matter and dark energy. Talk about a cosmic reality check, right?
Totally. It's both exciting and a little bit, well, unnerving. Exciting because there's so much more to discover out there, but also a bit unnerving because it really highlights just how much we don't know about the universe. It's like we're just starting to scratch the surface.
I think that's a great way to put it. It really underscores the vastness of our cosmic ignorance, but that's what makes studying the universe so amazing. Each new discovery leads to even more questions, pushing the boundaries of human knowledge further than we ever thought possible.
I love that. So next time we're looking up at the night sky, seeing that familiar band of the Milky Way, we can remember that we're only seeing a tiny part of something much bigger, much more mysterious. A universe shaped by forces we're only beginning to understand. Thanks for joining us on this incredible deep dive into the Milky Way. It's definitely given us all a lot to think about.